we have an object moving in a vertical circle, we can analyze the motion of that object regardless of where it is in that vertical circle. Maybe the object is at the bottom of the circle. Maybe it's, I don't know, 2/3 of the way up the circle on this side. Maybe it's at the top of the circle. Doesn't really matter. We can analyze its motion. And the motion of the object is going to be different depending upon where it is because forces are acting in different directions. We're going to focus on two places, however. We're going to focus on the top of the circle and the bottom of the circle. The reason we're going to do that is because those are our extremes. If we're talking about forces acting on objects, the extremes of those forces occur when the object is right here and when the object is right here at the top and the bottom of the circle. So even though we could analyze it on the side using a two-dimensional analysis, we won't because there's not really any need of analyzing it on the side. Now, in both cases here, the top and the bottom, there's two forces acting on the roller coaster car or the bucket of water that's swinging above my head or the keys that are swinging above my head. What are those two forces? Matt, what's one of those forces? Good. Which way does it act? Both times? Both cases here? Okay, so gravity acts down right here, and gravity acts up right here. I'm sorry, I'm not sure what you're saying. Yeah? Oh, so gravity's down. So basically what you're saying is gravity's always down. Good. Yes, it is. Gravity is always down. Good. What's the other force? It acts in both of these. Yeah, Dom? The normal force. Good. Which way does it act in the first case? Right here? Okay. What about relative to the ground? Which way does gravity act? Which way does gravity act relative to the ground? Always, Matt. Good. Which way does the normal force act relative to the ground? No. Down. Look, it's downwards. Don't make it harder than it has to. Sideways, he says. Don't make it harder than it has to be. Don't say all relative to the car or whatever. Okay, if you're sitting in the car and you're upside down, it looks like the normal force is up. Okay, but forget about that. Okay, look at the picture. Which way is it? It's down. And it's going to be down when you're at the top of the circle. What about the second case? Relative to the board, relative to the paper in front of you, which way does the normal force act here, Caitlin? It acts up. Good. It's going to be a bigger value than the force of gravity. We know that because that force toward the center of the circle must be bigger, otherwise it isn't going in a circle. Next step, hey, same as we did 100 times literally or more in our second unit, dynamics. What's next? We're going to say in both cases here, regardless of which diagram we have, F net is equal to the sum of the forces. F net is equal to Fg plus Fn. Now we're going to replace F net with something. Okay, we did this 100 times back in our last unit. This time it's going to be slightly different, but almost the same. It was m times A. Now it's m times, Elizabeth? Good, m times v squared over r. Now in the end, that's still m times a, but it's a very specific form of m times a. Centripetal force, the net force, the centripetal force, is equal to gravity plus the normal force. Still the same for both of those diagrams. Once we plug in numbers, though, we have to worry about signs, positive and negative. What about gravity? Gravity going to be positive or negative in diagram number 1? Matt. Is gravity going to be positive or negative in diagram number 1? Yeah, because it's down, right? Tom, is gravity going to be positive or negative in diagram number 2? Good, because it's down. Gravity is always going to be negative. In the context of these questions, gravity is always going to be negative. Now, what about the normal force? Grace, which way is the normal force acting at the top of the circle? That's right? Good. Because it's acting down. And at the bottom of the circle, Merrick, which way is it acting? It's positive because it's acting upwards, right? And finally, the centripetal force, mv squared over r, the net force, which way does it act when you're at the bottom of, when you're at the top of the circle there? Nick, which way does the centripetal force act at the top of the circle? Why? Help me there, Nick? The other Nick? Why? Good. When you're at the top of the circle, the centripetal force that acts toward the center of the circle is acting downward toward the center of the circle. When you're at the bottom of the circle, the centripetal force acts up, so we're going to make it positive. Now, my suggestion when you're rearranging this and solving for a variable other than, Fn, if you got to solve for V or M or some R, something like that, my suggestion is plug your numbers in and then rearrange. I very rarely say that. I almost always rearrange before I plug numbers in. But in this case, in this equation, I think it's easier if you plug your numbers in first. Not because the math of rearranging is easier, but I think it leads to less confusion on positives and negatives. There was a couple people in the last class, as we were going over a homework question, said, oh, I got mixed up with the positives and the negatives. And I said, did you rearrange it before you plugged your numbers in? Yes. Okay, that's why you got mixed up with positives and negatives. Okay, you increase your chances dramatically of making a mistake if you do it that way. So let's plug our numbers in and then rearrange it, and then we don't have to worry so much about the positives and negatives. All right. You had 2 questions for homework 1 and 3 on page 264. Do we need to go either of those? Okay, number 3 it is. A 0.98 kilogram rock is attached to a rope spun in a vertical circle. The tension of the rope when the rock is at the top is 79 newtons. What's the speed of the rock? Here's the rock. I don't care whether you draw that rock as a circle or a square. Draw it as a roller coaster car for all I care. In the end, the object at the top of the circle experiences the same motion, whether it's a rock or a roller coaster car or a bicycle or whatever the case may be. It doesn't make any difference. So draw it any way you want. We have a force of gravity acting at the top of the circle. We also have a normal force acting at the top of the circle, and it's also acting downwards. We're going to say F net is equal to the sum of the forces. That's going to be Fg plus Fn. We're going to say mv squared over r is equal to m times g plus Fn. What are we looking for here? The force of tension. No, sorry, we're looking for the speed of the rock, right? We're looking for v. Let's plug some numbers in. M is 0.98 kilograms. V is what we're looking for. Remember, we're plugging in the numbers before we rearrange. R was 0.40. 0.98 times 9.81. Plus the normal force. What exactly are we looking for in this question? Wait, we know the normal force. We said that. It was 79 newtons, right? Let's worry about the signs here. Gravity, which way is it? Gravity, Matt, which way is it? Up or down? Good, so it's positive or negative? Good. What about the normal force? Ali, the normal force here, positive or negative? Yeah, because it's downwards. Good. And what about the centripetal force? Even though I haven't plugged in numbers for all of the variables in centripetal force, once I start, I got to worry about positive or negative. What is it? So what is it going to be? Positive or negative? Why is it negative? Good. So let's try to simplify this a little bit. I'll pull out the calculator to do this. Let's say 0.98 divided by 0.4 gives me a value of 2.45. So I get negative 2.45 times v squared. 9.81 times 0.98. Gives me negative 9.6138. Subtract 79 newtons. So let's combine these two numbers on the right-hand side. That gives us negative what? 88.6138. Let's take the negative 2.4 over by dividing. Do that, we get 36.16889. Negative by negative is positive. Now I got to square root that. When I do that, I get 6.0 meters per second. Good? Yesterday I swung my keys around above my head, and we found that there was a minimum speed necessary to keep those keys in orbit around my head. If I went too slow, the keys wouldn't go in a vertical circle. We did the same thing, similar with water at least. As we swung it around fast, we realized that the water would stay in there. It had enough inertia to keep it away from the center. It wasn't like it was being pushed to the outside. It wanted to go in a straight line, but it didn't go in a straight line because of the centripetal force pushing it in. That centripetal force wasn't enough to cause the water to fall out, even when the water was at the top of the circle. But if I was going too slow, at some level, we all intuitively know that the water would have fallen out. So as I swing my keys, same deal. Swing it fast enough, the keys stay in the circle. Swing it a little slower, the keys will fall out of the circle. They won't go around the circle. There is a point at which, above which, the object will stay in a circle, below which it won't. In other words, there is a minimum speed necessary to keep the keys going in a vertical circle without falling out, to keep the water in a vertical circle without falling out, to keep the roller coaster car in a circle without falling out. How do we find that minimum speed? Well, I want you to watch real carefully at my keys as they swing around. Clearly right now they're going faster than minimum speed. There's no issue with these keys staying in a vertical circle at all. They're not going to fall out at the top, and we all know that. As I slow down, they're still staying in a circle, okay, but we're less confident that they're going to stay there. As I slow down even more, they still stay in the circle. As I slow them down more and more and more and more, gravity's not changing. What's changing in that situation in terms of forces is how hard my hand is pulling. As I slow it down, I don't have to pull as hard, right? That makes sense, right? Swing it around in a circle slower, I don't have to pull on the keys as hard. At some point, here they're going the minimum speed now. They're barely staying in the circle. Slower than that, they won't stay in the circle. Above that, they'll stay in the circle. How hard do I have to pull right now at the top to keep them in a circle? Watch these keys again. We'll slow it down. Super slow motion physics demo here. Okay, keys going around. Right now they're going fast. I have to pull. Gravity helps pull it down, but I have to contribute to the downward motion as well with my normal force. Okay, going fast enough, I got to pull down. But if I go slow enough, look what happens. Look at the string that holds the keys, the lanyard. How hard is it pulling right now? What's the tension in that lanyard? Oh, I thought you were answering that. Zero. Zero. So if you go too fast or faster than the minimum speed, then you're going to find that gravity helps pull it down toward the center when you're at the top, but you have to contribute to that. You have to add to gravity by pulling with your hand. If you go too slow, then gravity's too strong and it actually falls out of the circle like this. But if you go at just the right speed, gravity is sufficient enough to keep it in a circle, but not too strong to cause it to fall down out of the circle. So that means that at that point, when you're going at just the minimum speed, okay, the minimum possible speed, then you'd find that gravity does all the work. You don't have to pull down on the string at all. Therefore, the tension in the string or the tension in the lanyard would be zero. So here's what I want you to remember. When solving for minimum speed, you want to make Fn the normal force, whether it's supplied by the track in the case of a roller coaster, or the lanyard in the case of the keys, or my hand in the case of swinging the water above my head upside down. Doesn't matter. When you're solving for minimum speed, you're going to set Fn equal to zero, the normal force equal to zero, because gravity does all the work for you, and you're going to solve for V. So let's try this. The question 5.6 on 262 says, you got a 700 kilogram roller coaster. Seems pretty heavy, but it's not out of the realm of possibility at all. In fact, I'd be willing to bet that a real roller coaster, a real full-size roller coaster, has a roller coaster cart that's even heavier than 700 kilograms. Full of people, goes around a vertical loop that has a diameter of 50 meters. This is probably a red pennable thing. Draw attention to diameter because we don't want diameter, we want radius. Going to have to remember to divide that by 2 later on. What minimum speed must the roller coaster car have at the top of the vertical loop to stay on the track? Look, if it's going to fall out, it's going to fall out at the top, right? You're not going to be going on the bottom and all of a sudden fall out of the loop. So we're going to analyze the top. At the top of the circle, there's two forces usually acting. There's the normal force, or force of gravity, I should say, acting down. And then, of course, we have the normal force acting down as well. We're going to say, just like we have in all our other problems, the net force is equal to the sum of the forces. mv squared over r is equal to the sum of the forces. But before I do that, there's something I can do to simplify it when I'm finding minimum speed. What is that something? What can I get rid of here when I'm trying to find out the minimum speed possible to stay in this loop? Michael? Fn. You go faster than the minimum speed, then the normal force has to contribute when you're at the top of the loop, contribute along with gravity to the force acting down toward the center. Below the minimum speed, gravity is too strong and it just falls out of the circle. At the minimum speed, it stays in the circle, but gravity is sufficient at that point to keep it in its circle by itself without the need for the normal force. All right, so let's go to the next step. mv squared over r is equal to the force of gravity. Masses actually cancel here, which tell us, basically, look, the roller coaster was 700 kilograms. It could have been 1,000, wouldn't have made a difference. This may make you feel more comfortable when you go on the roller coaster ride on May 29th for your field trip. You can sit beside somebody who's 110 pounds, or you can sit beside somebody who's 350 pounds. You may lose a little bit of wiggle room if you're beside the bigger person, but in the end, you have no more chance of falling out of the vertical loop when you're upside down with a 350-pound person than you do with a 110-pound person. Why? Because mass cancels. Let's plug some numbers in here. The speed of this roller coaster car is, that's what we're looking for actually. The radius is 25 meters. G is 9.81. Now we're going to stick a negative in front of both of these because when you're at the top of the circle, of course, gravity is down, as is the centripetal force down. As it turns out, because it's in both terms, you could actually cancel the negatives and just make it positive. Okay, we're going to put them in there because we want to be consistent. Every time it's down, we make it negative. Let's take the 25. Actually, let's take the negative 25 up by multiplying. We get 245.25. Negative times a negative, negative 9.81 times negative 25, positive 245.25. Square root that. And when we do, we get 15.66. We're going to round that to 15.7 meters per second. So what we're saying here is this. If this roller coaster car, something happens, it's going 15.6 meters per second, watch out. You don't want to be in that car because it's going to fall out of the loop. Now, it's not going to fall straight down. The closer it's going to the minimum speed, the better off you are because the closer to the track you'll stay. But it's still not going to stay on the track at 15.6. Anything below 15.7, it falls out of the loop. Anything above 15.7, it's fine. Doesn't matter whether you're going 16 or 19 or 50 meters per second, you're going to stay in the loop just fine. Now, the faster you're going, the more G forces you're going to feel as you're going around that loop, but you're not going to have any less chance of falling out of the loop with more force, as long as you're above that speed. Yeah. Well, this is a rounded number, but let's assume that the number is exactly 15.7. Then that would mean at 15.7 you would stay on. Below 15.7 you would fall off. The minimum speed is the speed at which you barely stay on, not the speed at which you begin to fall off. So, I mean, there's some semantics in the question there, right? We're not going to lose any sleep over that. But in the end, I'm not going to ask you a question on a test that says, that's trying to trick you that way. Minimum speed or, is it below that or exactly that number? If I ask you for the minimum speed, this is what it is. Okay? Got it? Take a look at those two questions, please, on page 262 and see what you can do with those.